Watch these words for a moment. They're drifting across an empty plane, searching for somewhere to settle. In just a second, 4 of them will lock into a shape that should feel a little uncanny. There, king, queen, man, and woman have snapped into place, and the 4 of them form a clean parallelogram. That is not a coincidence, and it is not something anyone drew by hand. The geometry came out of the meaning of the words themselves. The promise of this video is to explain how that shape can possibly exist. How do you take something as slippery as the meaning of a word and turn it into a point you can plot? By the end, you'll see why turning language into geometry is exactly what lets a machine act like it understands us. Let's start with the problem. To a computer, a word is just a string of characters. The letters CAT carry no more built-in meaning than a random serial number. Nothing about the symbols tells the machine that a cat is furry, or alive, or anything like a dog. One tempting fix is to give every word its own number. Cat is word 5842. Dog is word 5843. But that's a disaster in disguise. Those numbers are neighbors purely by accident, and the machine would wrongly think 2 words are related just because their IDs happen to be close. So a single number is too poor. What if instead of one number, we gave each word a whole list of numbers? Not an accidental ID, but a set of coordinates that place the word somewhere in a space. That list of numbers is what we call a vector. Here's the key mental shift. A vector isn't just a list, it's an address in space. 2 numbers are an address on a flat plane. 3 numbers are an address in a room, and the whole game of word embeddings is choosing these addresses so that a word's location actually reflects what it means. Let's make that concrete with a toy example. Imagine we only care about 2 qualities, how living something is and how large it is. Then every word gets just 2 coordinates, and we can plot it on a plane we fully understand. So a mouse is very alive but very small, down in one corner. An elephant is just as alive but enormous, up high. A rock is largish but not alive at all, off to the side. Already similar things are landing near each other without us ever stating a single rule about similarity. Add a few more. Cat and dog land close together, both medium and alive. Whale drifts up toward elephant, and notice what's happening on its own. A cluster of animals is forming in one region of the map, just from their coordinates. This is the whole idea in miniature. Meaning becomes position, and similarity becomes nearness. If you can arrange words so that closeness in space means closeness in meaning, a computer can finally reason about words using nothing but geometry. But 2 dimensions can't capture everything. Aliveness and size say nothing about whether a word is a color, an emotion, or a country. Real meaning has far more facets than we could ever draw on a page. So real embeddings don't use 2 numbers, they use hundreds. A typical word vector might have 300 coordinates, each one a different subtle dimension of meaning that the system discovered on its own. We can't picture 300 dimensions, and that's fine. The math treats them exactly like the 2 we just used. Still coordinates, still an address, still distances between points. Everything we learn in 2D carries straight up into 300D unchanged. Now the real question. Nobody sits down and handwrites 300 numbers for every word in the language. So where do these coordinates actually come from? The answer is a beautifully simple idea about language. The idea is this: you shall know a word by the company it keeps. Words that show up in the same kinds of sentences tend to mean similar things. If 2 words are surrounded by the same neighbors again and again, they're probably related. Take cup of blank in the morning. Coffee fits, tea fits. Both live in that same slot across millions of sentences, so the system concludes they belong near each other. It never needs a dictionary, it just needs to read a lot of text. So the training works like a giant guessing game. The model slides a window across mountains of text and repeatedly tries to predict a word from its neighbors, or its neighbors from the word. Each guess is a tiny quiz with a right answer sitting right there in the sentence. At the start, every word's vector is just random numbers, so the guesses are terrible. But each mistake gives a direction to nudge things. Push this word's vector a little closer to the words it actually appears with, a little farther from the ones it doesn't. Do that billions of times, across billions of sentences, and something remarkable happens. The random cloud slowly organizes itself. Words that keep sharing context migrate together, and the whole space settles into a map of meaning nobody explicitly designed. Let's actually look at that finished map. Since we can't see 300 dimensions, we use a projection, a way to flatten a high-dimensional space down to 2, like casting a shadow of a sculpture onto a wall. The projection isn't perfect. Some information is lost when you flatten anything, but it's honest enough to reveal the big structure. And when we project a real trained embedding, the structure is striking. Here is a cluster of animals, all huddled in one corner. Over here, a tight group of countries. Down there, a knot of verbs. Each region formed because those words truly do keep similar company in real language. And the clusters aren't just blobs, they have internal order. Within the countries, capitals sit in a consistent relationship to their nations. Within animals, sizes and types arrange sensibly. The map has structure at every scale. That internal order is the doorway to the most famous trick in all of word embeddings. Because if directions in this space are consistent, then moving in a direction should mean something. Let's test that idea directly. Come back to our 4 opening words, king and queen, man and woman. We're going to treat these words not as points but as arrows from the origin, because that's what a vector really is, a direction and a distance. First, look at the arrow from man to woman. It points in some direction and has some length. Now look at the arrow from king to queen. It's essentially the same arrow, same direction, same length, just starting somewhere else. That shared arrow is a concept made geometric. It's the male to female direction, and it looks the same whether you start from a commoner or from royalty. The embedding discovered gender as a consistent direction in space, entirely from context. Now we can do arithmetic with meaning. Start at king. We want to strip away its manness, so we subtract the vector for man. Geometrically, subtracting means adding the reversed arrow, walking backwards along that direction. King minus man leaves us at a kind of pure royalty, a genderless monarch floating in the space. It isn't quite any single word, but it holds the essence of ruler with the maleness removed. Keep your eye on where we've landed. Now we add the vector for woman. We attach the woman arrow, tip to tail, and walk forward along it. This pushes our genderless royalty in the female direction, the same direction we found earlier. And where do we land? Almost exactly on queen. King minus man plus woman equals queen. Not as a metaphor, but as literal arrow addition on a map the machine built by reading. The parallelogram from the opening was this equation all along. Let that sink in. We did algebra on meaning. The same trick works elsewhere. Paris minus France plus Italy lands near Rome, because the capital of relationship is its own consistent direction too. Now, an honest caveat. These results are cleaner in diagrams than in reality. The real vectors rarely land perfectly on the target. They land nearby and we pick the closest known word. But that they land close at all is the astonishing part. This raises a practical question. We keep saying words are near or far, close or distant. But in a space with hundreds of dimensions, how do we actually measure how alike 2 words are? We need a real definition of similarity. You might reach for plain distance, the straight line between 2 points. But that has a flaw. A very common word can have a long vector and a rare word a short one, even when they mean similar things. Length can mislead us. So instead of distance, we look at angle. 2 arrows pointing the same way are similar no matter how long they are because they share a direction, a shared blend of meaning. The angle between vectors is what we really care about. This is called cosine similarity. When 2 words point in nearly the same direction, the angle is tiny and the cosine is close to 1, very similar. When they're perpendicular, the cosine is 0, unrelated, and when they point opposite ways, it's -1, opposites. The name just comes from trigonometry, the cosine of the angle, but you don't need the formula to feel it. Small angle means aligned, meaning means high similarity. Cosine similarity turns how alike are these 2 words into a single honest number between -1 and 1. Now we can watch the machine use it. Give it the word happy and ask for the nearest directions. It scans the space, computes cosine similarity to everything and returns joyful, glad, delighted. It found synonyms without ever being taught what a synonym is. This is the quiet engine behind so much of modern language technology. Search that understands what you meant, not just the words you typed. Recommendations, translation, spam filters, the first layers of chatbots. Underneath, they're comparing vectors and measuring angles. Let's step back and ask what understanding even means here. The machine has no experience of a cat, no memory of fur or purring. What it has is a position, and a web of relationships to every other word, meaning for the machine is location. And maybe that's less alien than it sounds. We understand things relationally too. You know what left means only in relation to right, what warm means between hot and cold. Meaning has always lived in the relationships, not in isolated symbols. We should also be honest about the flip side. These vectors learn from human text, so they absorb human biases along with meaning. If the training data links certain jobs to certain genders, those associations become directions in the space too. The geometry is only as fair as the language we feed it. But the core achievement stands. We took meaning, the most human and abstract thing, and gave it coordinates. Once meaning has coordinates, it has geometry, distances, angles, directions, arithmetic, and geometry is something a machine can compute all day long. So return one last time to that opening parallelogram. It looked like magic, 4 words forming a perfect shape. Now you know it's the visible tip of a vast structure, where every word is an address and every relationship is a direction you can walk. Turning meaning into geometry is the quiet trick that lets machines act like they understand language. Not because they feel what words mean, but because they've learned where words live and how far apart. And in that space of directions and distances, understanding starts to look a lot like arithmetic. If this made it click, subscribe for more visual math.